So we're continuing. So we have identified a few sections here. This intersection that is the boundary between plastic and failed regions, the bound B and C that are the boundaries between the elastic and plastic region, and D is the other, on the other side is the boundary between failed and plastic region. As I explained earlier, in this region, sigma is constant from equilibrium, and because it's 0 here, it has to be 0 here. That is this in 1. Now, in B, in this region, it goes up with this slope, and the length of the region in this region is L2, AB is L2, so sigma 1 of B at this point is going to be 0 plus tau F over B times L2. This is in 1. In 2, we have kind of the mirror effect of this. Basically, here is sigma 0, here is sigma 0, and it goes down linearly as tau F over B. I have to multiply it by L, and the negative sign is because it goes down. So, therefore, basically, in this region from here to here, I can assume that sigma 1 is varying linearly, and so the equation for that is going to be here. Sigma 1 of x prime is going to be sigma 1 of B times x prime over L2. This equation is only valid for the plastic region, because in the plastic region, we can expect a linear relationship between sigma 1 and x, or x prime. And now it's, when I say plastic, it's the mortar that is deformed plastically. Throughout this conversation, throughout this lecture, I mean, all of this bio-inspired material, we're going to assume that the mortar, the brick remains elastic up until failure. Elastic modulus of that is this guy, is E. So the stress, this is the stress in the matrix, in the tablets or bricks, is equal to the product of the strain in the tablet times, or brick times the elastic modulus. And instead of a strain, I can write du dx prime. I can do the same, very similar argument for sigma 2, which is, in this case, it's going to be this. Here, the variation of sigma 2 with x prime is linear, but with a negative slope, because the direction of tau is the other side. So basically, I call this equation equation 12, and this equation equation 13. If I subtract these two equations from each other, and the reason I want to do that will become clear in a second, is because on the left-hand side, basically when I am subtracting the equation here, let me move my, okay. When I'm subtracting this from that, I can factor out e's, and I can take it to the other side, and I can have du1 minus du2 over dx. And keep in mind, I can write this as du1 minus u2 divided by x prime, and u1 minus u2, I hope you remember, is nothing but gamma times h. You remember that gamma was u1 minus u2 divided by h. And h here is constant. So I can take this to the other side, and I can have gamma times h is equal to u1 minus u2. So my equation becomes d gamma dx prime times h is equal, and this side of the equation is the same as this side of the equation. Now, one thing I want you pay attention to, do not ever forget, is that this analysis is only valid for the plastic region in the matrix, because only in the plastic region I can bring this linear dependence on x prime into the picture. But also keep in mind that this relationship will always hold. This is our compatibility relationship. The strain in the mortar is equal to, the shear strain in the mortar is equal to u1 minus u2 divided by h. But there are two very interesting things that I want you to pay attention to. So this equation here, equation 14, applies in this boundary, right? Let's see what this boundary tells us about gamma. This is what I want you to pay attention to. So this equation, this equation is valid. If I go back to page 11, this equation is valid from here to here, or from here to here, doesn't matter. But at this point, this is the border between plastic deformation and failure. So right at this point, gamma is equal to gamma f. Right at that point. And this point is the border between elastically deformed and plastically deformed. This is the point that yields. This is the boundary that the yielding starts. So this here, gamma, is nothing but tau f over g, right? So basically, so I have two boundary conditions for the differential equation that I've derived. Let's go back to the PDE. I'm sorry, ODE. This is my ODE. Okay, and this is a first order. That's the first order ODE. So it has to have one boundary condition, but we have two boundary conditions. And the reason for that is that there are other parameters in the ODE that I don't know. For instance, I don't know what, I do not know what L2 is. My sigma B, the sigma 1 at B, depends on L2 as well, but I don't know what that is. Okay, so so basically it's, and the other thing is, I defined a parameter x prime, but in reality, I don't know where to start the x prime from. It was a mathematical convenience that I replaced my coordinate system, but which allows me to derive or move this analytical solution forward, but doesn't let me solve it completely. So it is an ODE with unknown parameters. That's why I have two boundary conditions that I have specified here. This is what we call equation 14, and equation 14 is first order in terms of x prime. It can be integrated. First, I use the boundary, and this is based on x prime. So gamma of x prime is equal to gamma f. When I apply this boundary condition, gamma x prime becomes this, And you can easily see if I set x prime equal to 0, it gives me gamma x prime equals to gamma f. And also, if I use the second boundary condition, that allows me to calculate L2. So basically, let's pause here. And